when we started the conference, it was clear that we wanted to have DeepMind at the conference. You know, you cannot do something without them today. I think most of the big labs have been created by ex-DeepMind. That being said, we tried to contact Google friends, and they told us there is no way you can have someone from DeepMind. I mean, they don't do conference anymore. We tried with Google UK, same thing. And then, I think after a few weeks, someone from Google Belgium came back to us and told us, okay, guys, we have this Belgian scientist. He's also a director at DeepMind for 11 years. So he saw some shit. And he's from Belgium, so he's from Ghent. He can be in Brussels for your conference. So if you're still up for it, please invite him. And of course, today, that's why we are super happy to have Sander. Sander, please welcome on stage and have fun.
Hello, everyone. So this is going to be a little bit technical. I hope you're up for that. I try to make things accessible, so I'm going to focus on the intuition behind things, but it is going to be a little bit technical. So this is going to be about image and video generation models, because that's what I work on at DeepMind. Before I get into that, though, I want to briefly talk a little bit about my background, because I've been asked to do that, because I am from Belgium. I studied in Belgium, and I moved to London to join DeepMind. I did my PhD at Ghent University from 2010 to about 2015, 2016, depending on who you ask. This was under the supervision of Benjamin Schrouwen, which some of you might have heard of. He's more known these days, I think, as a serial entrepreneur, but he also had a brief but very successful career as a university professor. And actually, his group at Ghent University produced 7 PhDs that still work at DeepMind today. So he did a pretty good job there as well. So yeah, this is a bit, just a little bit about my background. So I did my PhD on AI for music, and then did a brief internship at Spotify on music recommendation as well. Then I joined DeepMind in the summer of 2015. The AlphaGo project was in full swing, so I had the opportunity to make a small contribution to that, which was very exciting. And then I sort of switched my focus to generative AI. But this was 2016, so there wasn't a lot going on in generative AI yet. The images that we were generating were sort of 32 by 32 pixels, sort of stamp-sized, and we were very proud when that looked vaguely like a human face, that kind of thing. And then, yeah, I guess more recently, in the last few years, this has kind of suddenly started working. And so obviously my day-to-day job has changed a lot as a result. I was sort of doing blue sky research before. Now we are building flagship products that go into, flagship models that go into Google products. Cool. So I have a blog. So basically almost all this, the content of this presentation is sourced from that blog. So I try to explain how generative models work in an intuitive way. And this is, the last few years has been mostly focused on diffusion models because that's what I work on day to day. So yeah, all you have to remember is sander.ai, all these blog posts are on there. So I'm going to try and give you a whirlwind tour of sort of 8 different aspects that go into building image and video generation models at scale. So it's going to be very concise, very fast. I do actually have a slightly longer version of this talk on YouTube, so if you want more information about some of these things, you can just type my name into YouTube and it should come up. So let's start with data. That's where it all starts. Obviously, data curation is just a very important aspect of all of this. To the point where I think, obviously, sometimes time spent on making the data better is probably better spent than sort of trying to make the model better, trying to tweak the model architecture, things like that. This is actually something that a lot of us researchers with academic backgrounds were not taught, right? Because we were told to basically focus on making the models better and always using the same sort of prepackaged data set to evaluate our models so that we could compare them to the state of the art. So that's very different in industry where actually spending time on data is probably the most important thing. That's all I'm going to say about that, though, because obviously there's a lot of secret sauce there. So I can't talk about the details of exactly what we do. But trust me that it is very important. The next question is, how do we represent this data when we feed it into models? Like digital representations of images and video are typically pixels, right? Grids of pixels. But these grids can get very massive. So if you, the example on the slide here is of a small image, but let's say you have like 10 seconds of 1080p video at 30 FPS. If you store that in like a raw pixel format, we're already talking about more than 1 gigabyte of data, right? And so we have to feed that into these models. We don't tend to do that in the form of pixels. We tend to use something called latent models. So they operate on latent representations rather than directly on pixels. And the way you can think of these latent representations is it's just compression, right? It's just a form of image compression, video compression. But it's a form of compression that's adapted to the use case of building generative models. Because we cannot just use pre-existing compression algorithms like JPEG and H.264 and things like that, because they destroy too much structure in the signal. And all of our generative models have a lot of very important inductive biases that sort of rely on there being very specific topological and statistical structure in these signals. And so that's why it's very important that we sort of build our own compression mechanism. And usually we do that by training an autoencoder. So we sort of spatially spatially or temporally compress the signals, and then we usually go from like 3 RGB color channels to like having more channels to sort of compensate for the reduction in spatial temporal resolution. So that's sort of what I'm trying to demonstrate on this slide. And then if you look at like what these latents actually end up looking like, what these compressed representations actually end up looking like. So this is from a paper called EQVAE where they sort of try to visualize this. And what I want you to take away from this slide is like if you look at these visualized latents, you can still tell what's in the image, right? You can still tell what the animal is. That large-scale structure has not been changed. It's not been compressed. It's still there in the way that it was in the original image. It's really only the low-level structure, the textures and things like that, that are maybe represented in a slightly higher-level way. So I like to call these latents. I actually think latents is a very poor name for this thing, because latent sort of implies, a high-level underlying variable that we can't. That we can't measure, but actually these latents are just fancy pixels. That's what I'd like to call them. They're just slightly fancier pixels. So that's what goes into the model. And then the question is, how do we model these things, right? Because we could use autoregression, like we tend to do with large language models, but actually the dominant approach right now for visual data is diffusion. And I want to just give you a very briefly, if you're not familiar with diffusion, or even if you are familiar, I just kind of want to give you a brief sort of overview of the intuition behind why this actually works. So diffusion is basically an iterative refinement mechanism that's based on iterative denoising. So you can think of language models doing iterative refinement by sort of serializing the sequence to generate, or the data to generate in a sequence of tokens, and then generating one token at a time, right? So you're training the model sort of one token at a time, but of course when you use the model, you're sort of chaining these generative steps together. And so that's an iterative generative procedure. And diffusion kind of does a similar thing, but here we're going to construct these steps through a denoising mechanism. So we're going to basically add noise to an image very gradually, add a little bit of noise at every step, until eventually the image kind of disappears, all the information is gone, and then we're just going to train a neural network to denoise. We're just going to give it a noisy image and ask it what was the clean image that gave rise to this particular noisy observation. And it turns out you can do generative modeling this way. And so I want to briefly explain how that works. And to do that, I have this diagram. So I have these images that I'm going to sort of visualize with points in a 2D space. Of course, images are actually very high-dimensional objects, so keep that in mind. I only have 2 dimensions on my slide, but I'm actually talking about stuff that happens in a very high-dimensional pixel space or latent space. So we have this original image, which I call x0. That's a clean image from our data set. And then I've sort of artificially added noise to it. Like I've sort of constructed a noisy version of it, call that xt. T is just a random time step in our process, in our diffusion process. And then what is the diffusion model actually going to do? It's going to try to denoise this image. And so it's going to try, given the noisy image, it's going to make a prediction of what the clean image might have looked like. And what you're typically going to see is this is going to be a blurry image. Because obviously the noise that we added has destroyed information, right? So the model cannot exactly know what the original image was, but it can sort of make an attempt at predicting what it might have been. And there's actually many different possibilities. But we're asking the model make a single prediction. So it has to just predict the average of all these possibilities. That's the only thing it can do. So that's why you end up with these blurry predictions. And so I like to think of it as these models not sort of trying to predict an image, but rather trying to predict a region of image space where the original image might have come from. And that's what I'm trying to visualize here. Right. And then once we have that prediction, we just take a small step in the direction of that prediction. And this you can compare to how we optimize neural networks, right? In weight space, we calculate gradients, we take small steps in the direction of these gradients. We do that many times over and over, because if we try to take large steps, that actually doesn't work, because that gradient direction is only valid locally. And it's the same thing here. If you would take a large step, you would just end up with a blurry image. That's obviously not what we want. So we take a small step in that direction, and then we get a slightly less noisy image. And then typically what we do in diffusion sampling, which is different from optimization, is we actually add a little bit of new noise back. So we just removed a bit of noise, and then we add a little bit of noise back, which might seem counterintuitive, but it actually sort of robustifies this procedure. Not all sampling algorithms do this, but many do, and it sort of makes it more robust against its own mistakes, basically. And then we just repeat the process. Like now we're in this new, sort of slightly less noisy image, in a position in image space, and then we just make a new prediction. And that prediction is going to be slightly different now, because obviously we're starting from a different starting point. It's slightly less noisy, so there's slightly less ambiguity, and so our prediction actually corresponds to a smaller region of the input space, because there are fewer possibilities now, like where the original image could be. And then, rinse and repeat. That's kind of the idea. You do that for a bunch of steps. You end up with an image that looks like it was drawn from your data distribution. Cool. So next, let's talk about model architecture. How do we construct these denoisers? There's sort of a bit of interesting history here, but because historically we used something called UNets. So we needed a network architecture that would take in an image and predict another image. Right? This is kind of different from classical computer vision networks, which would take in an image and then predict a label or something like that. But here we needed to predict an image as well. And so we looked actually at the segmentation literature, because they were also predicting outputs that had the same topological structure as the input. And so we basically stole this architecture from a biomedical image segmentation paper, and this turned out to work really well for denoising, for diffusion models. But of course, these days everyone just uses transformers, because that works even better and that scales better. Just like you can use transformers to generate sequences autoregressively, you can also use them to denoise images, and they work really well for that as well. So yeah, it's all transformers these days. Then in terms of how we train these things, the one thing I want to say is that obviously scale matters a lot, also for image and video generation. I would say maybe a little less at this point than language models. Language models are generally much larger still today than image and video generation models are. I'll talk a little bit more about why that is in a bit as well. But yeah, so we basically want to try and parallelize over as many chips as we can. Obviously, you can do that in different ways. You can sort of split your batch of training data across the different chips and sort of do data parallelism. But also more and more we do model parallelism, right? We sort of try to pull the model apart and put different parts of the model on different chips. We extensively use JAX at DeepMind, which makes that really easy, kind of does it for you. You just do jax.pget around your function and figures out where to put everything. I'm sure PyTorch has similar things, but I've actually never used PyTorch because I've been on the inside at Google for over a decade. But yeah, that's kind of all I want to say about that. Yeah, now let's talk about sampling, because I've already kind of explained to you how you can use a denoiser to sample images. But actually, there's a very important trick that we always use called guidance, which I like to think of as kind of a cheat code for diffusion models. It kind of allows them to punch above their weight. And that's also maybe part of the reason why these models still tend to be smaller today than large language models. Because guidance actually works so well for this use case. I'll try to explain to you what guidance actually does, again with the same sort of type of diagram that I had before. So we're starting again with a noisy image, and we're going to make this prediction like before. But actually this time we're going to make two predictions. So I'm going to add another prediction here. The difference between these two predictions is whether I've told the model anything about what the image is or not, like whether I've given it a prompt or not, let's say, or some other kind of conditioning signal. That's indicated by the C there, so that's the conditioning signal. I can ask the model to make a prediction just by giving it an image, or I can tell it this is an image of a rabbit, and then ask it to make a better prediction. And it can actually use that information to sort of restrict the number of possibilities, right? So that conditional prediction, as we call it, is actually going to be slightly less noisy. Now what we can do with these two predictions is we can look at the difference between them. And if you look at this as in a vector space, that's just a difference vector, right? And the naive, simple trick of guidance is simply to say, oh, that's the difference between unconditional and conditional. Let's just amplify that. Like, just multiply that vector by a scale factor. And then this will define the new direction that we actually move in. And that's it. This is a trick that makes these models work way, way, way better. And it's like, it almost shouldn't work if you look at this. But actually, you can sort of analyze this, and there's like a whole Bayesian explanation for why it makes sense to do this, which I'm not going to go into. But I am going to show you the effect. So this is very interesting because, yeah, so that's the rest of the sampling procedure just proceeds as normal. I do want to show you the effect. And what's interesting here is I had to go back to 2021 to find a paper that shows samples without guidance. Everyone just leaves this on these days because it's so important for these models to perform well. And so people sort of have stopped appreciating just how important this actually is. But if you go back to 2021, there's a paper from OpenAI called Glide, and they have this really nice comparison of samples without and with guidance that show you what guidance actually does. So on the left, you have samples without guidance, and you can see they're more diverse, right? But they also kind of suck. You know, they're not that good. But then if you enable guidance, you get much better sample quality, but also the diversity collapses. And of course, that's a trade-off, and depending on the use case, that's a trade-off you might be willing to make, right? If you only need one image, you probably want one from the right. Here's another example with a different prompt, sort of showing the same thing. You get much nicer image quality, but the diversity kind of collapses. But this is a trick that basically all these flagship image and video generation models very heavily rely on to this day. All right, then if we want to deploy these models, one problem is that sampling is slow. So sampling is actually more expensive than for language models in terms of flops, because each step is like a full forward pass through the model over the entire canvas, so that's more expensive than language models where you would sort of do it token per token, right? So it's more parallel, but it's also more flops. So we try to distill these models to make them require fewer steps to produce good images. And as I said before, if you try to sample from a vanilla diffusion model in very few steps, you're just going to get blurry images. So you actually have to use some tricks to make that work well. Basically, the idea is of many of these methods is to sort of trace the path through input space that you would take during sampling. So like going from a fully noisy image to the final denoised image, you can sort of trace a line through the input space. And then the question becomes, rather than sort of predicting the tangent to that line, which is what a denoiser does, can we sort of characterize this line in a different way? And one way would be, for example, to just directly try to predict where we're going to end up, right? Can we train a model where from a noisy iterate we can sort of directly try to predict where this line is going to end up? Turns out you can do that. This is called a consistency model. And this idea is the basis for a lot of these modern distillation techniques. It's not the only way to do it, but it is a very popular way to do it. Cool. And then finally, the last thing I want to talk about is control. Like once you have this type of generative model, how do you actually make it do what you want it to do, right? And of course, the canonical way of doing that is just to provide a text prompt. That's how these models are sort of usually trained. They're trained with captioned images and captioned videos. So at test time, you can provide a new caption, and then it generates a video or an image with the desired contents. But that's not the only way to condition these models. And more we're seeing that people want a lot more. There's just some things that are really hard to express in textual form, right? Let's say you want to generate a video and you have a particular character that you want to feature in the video or a particular object. It's much nicer if you can just give the model an image or a short video of that material. And so we're also looking a lot at reference-based generation these days. And then in the case of video generation, there's a few types of conditioning signals that are sort of really hard to capture in text, like the camera motion throughout the video, things like that. So we're looking at sort of more advanced representations for conditioning there. A lot of this stuff can be done in pre-training, so you can sort of provide that data to the model in pre-training. But then often we find that we can sort of post-train these capabilities into the model afterwards. And that's often very useful, because often you have like a small annotated data set with, like, for example, camera motion information. It's quite nice that you can sort of feed that into the model after the pre-training is done. Okay, so yeah, this was very, very quick, very whirlwind tour, but I'm going to leave it there for now. Thank you very much for listening. And
thank you so much.